So let's close our class today with a discussion of how to generalize what we've done in one-dimensional quantum mechanics to 3D. So we began our study of quantum with the time-dependent Schrödinger equation, right? And so in 1D, right, we didn't originally write it in this form, but it really is that the Hamiltonian operator acting on the full time-dependent wave function, so psi of x t, right, equals I h bar d psi, capital Psi of xt dt, right? And so in the language of like 421, we speak of the Hamiltonian as the generator of infinitesimal translations in time. So naturally, how one might want to think about this in 3D is to now let the wave function depend on x, y, z and time, but keep the same structure. So we still have a Hamiltonian operator acting on x psi, which now depends on three positional variables in time, equals I h bar d psi d t. Then it becomes a question of, well, how do I generalize my Hamiltonian, right? Because in 1D, right, we have our Hamiltonian, it's really the total energy operator, so there's a kinetic energy term, right, and that went like px squared operator over 2m plus the potential energy v of x. Now, if we have, right, so that's the important thing, right, because this is really kinetic energy. If I have a particle that's moving in 3D, right, its sort of vector velocity, right, is going to, or the magnitude of its velocity is going to depend on not just the x component of its momentum, but also its y and its z component. So we might naturally be led to, in 3D, this kinetic energy term being, operator term really, being px squared plus, whoops, right, plus subscript, px squared plus py squared operator plus pz squared over 2m. So hopefully this is at least plausible, and that this, that this sort of the thing upstairs is the magnitude of the momentum if we were to replace the classical expression for momentum with the associated operator. Now, how do we get these operators themselves, px, py, and pz? We can go through a really similar process as we did to get p sub x, and then that, right, will lead us to, right, this ends up being so py operator equals I h bar partial y, so minus I h bar partial y, and similarly for the for pz, partial z. Hopefully this is all at least believable based on what we did in 1D. And now the other thing that will change in 3D is that, right, this, our potential energy, is now going to depend on x, y, and z. Okay? We're now prepared then to write down the full time-dependent Schrödinger equation in 3D. To save a little bit of writing, I'll write everything in terms of psi of vector r, where we assume r vector includes x, y, and z. But again, we'll think of the first a full position and time-dependent wave function, as would appear in the time-dependent Schrödinger equation. So let's finish off by writing out the Hamiltonian operator in 3D. So in 3D we have p squared, all three components over 2m, and that turns out to give us a factor of minus h bar squared over 2m. Now we have partial x squared plus partial squared partial y squared plus partial squared partial z squared. This would act on a wave function plus a potential energy V of r, where again r is x, y, and z. Now, those of you who have taken Calc 3 might recognize something familiar looking in here. What's this thing in the big parentheses? Hopefully, if you've had Calc 3, you might remember that this is none other than the Laplacian operator. And so I can actually rewrite this Hamiltonian as minus h bar squared over 2m times the Laplacian plus the potential energy. And so what we really see is that we've replaced the second derivative with respect to x with the Laplacian. We are now able to write down the full time-dependent Schrodinger equation in 3D. And it's going to look like this. So we have minus h bar squared over 2m. I'll write this in parentheses. Laplacian plus potential energy acting on my wave function. Oops, equals a positive IH bar. Partial psi, partial t. Now it turns out we can apply separation of variables in the same way as we did for the in 1D. So namely, we separation of variables leads us to write the full wave function psi of rt as a product of something that depends on position and something that depends on time. So we'll be able to write this as little psi of r times something time dependent. Not too surprisingly, it's just the same time-dependent phase factor that we've come to know and love. So e minus iet over h bar, where lowercase psi and e satisfy the time-independent Schrodinger equation, which is now the energy eigenvalue equation. So that turns into minus h bar squared over 2m Laplacian plus potential energy acting now on our position dependent, our lowercase psi of r, equaling the energy eigenvalue E psi of r. So in conclusion, there's really not too much of a change going to 3D other than everything depends on x, y, and z, and we replace the second derivative with respect to x in the Hamiltonian with the Laplacian. As a final example, I would like us to consider the 3D version of the infinite square well. This I can't really draw, because I'm not good at drawing in 3D, but imagine now just a three-dimensional box where the potential energy is 0 in a cubical region where x, y, and z are all between 0 and L, but infinite otherwise. And then this will point out this will let us see a couple of features that we'll see also in the hydrogen atom. Now, in the region where the wave function is non-zero, the TISE becomes minus h bar squared over 2m del squared psi of r equals E psi inside my box. So it turns out that we can further apply separation of variables on this piece. I think Townsend goes through this in the beginning of chapter 6 if anybody's curious. But it's really again, and what you end up being able to do is that you can separate the wave function into a piece that depends only on x, a piece that depends only on y, and a piece that depends only on z. So I'll call the piece that depends on x, capital X of x, and then we'll have capital Y of y, and capital Z of z. So it's a product. And then you basically end up turning this 3D problem into 3 independent 1D problems, each of which is equivalent to the 1D infinite square well. And it turns out that you can just write the answer down based on that. So what we get for the energy eigenfunctions is the following. So it turns out that, right, because you can fit different numbers of wavelengths in your box going in x versus y versus z. In 1D, we could just talk about size of n, where there is this quantum number n that told us, right, how many half wavelengths we could fit. Now in 3D, we need a separate n for x and y and z. So I actually have to write my wave function as psi of nx, ny, and z of r. It ends up being a product, so now it goes like 2 over L to the 3 halves. We have sort of 3 of those normalization bits, vectors up to the 3 halves. Now we got a sine nx pi x over L times my y-dependent part times my z-dependent part oh, my marker's dying. The eigenvalues so again, the energies will now depend on all 3 of nx, ny, and nz. E sub nx, ny, and z. Now again, sort of acts like the 3 1D wells, and it'll go like h bar squared pi squared over 2m L squared now times nx squared plus ny squared plus nz squared. So this is sort of a quick tour, and hopefully it's at least plausible, but there's sort of 2 physical features that I want to point out. In 3D, we need, first of all, 3 quantum numbers. We need 3 quantum numbers, or indices if you want to think of them. So here we have nx, ny, and nz. Things will be a little different when we look at the hydrogen atom, because it'll turn out we want to work in spherical coordinates. But the idea that we need 3 numbers to describe to fully describe a quantum state in 3D stays the same. The other thing that I want to point out is degeneracy. Right? In particular, there's more than one possible. What this means is that more than one set of nx, ny, and nz have the same energy eigenvalue. So in particular, right, if I look at this expression, right, I'll get the same energy eigenvalue if I have, let's say, nx equals 1, and y equals 2, and nz equals 1, as I would if I had, like, nx equals 1, and y equals 1, and nz equals 2. And similarly, right? That there are multiple sort of states that have different quantum numbers but still have the same energy turns out to be another feature of the hydrogen atom. And it's sort of one of the things that ends up happening when you go to 3 dimensions. Okay. So when we come back next time, we'll sort of see how this kind of idea applies to hydrogen. It's going to be trickier because for hydrogen, we'll need to work in spherical coordinates, and so that introduces some interesting things with regards to angular momentum. We won't do a ton of detailed deriving. That we'll have to save for 421. Townsend even leaves some of the details out because they get a little bit challenging. But we'll, I think, get enough of a sense of how the Schrödinger treatment of hydrogen works and how it's different from the Bohr model, and how it's also consistent with what we learned previously about quantum mechanics in 1D. I'll see you next time.